Hello everyone, this is Manohar Reddy, Assistant Professor, Department of CSC, Cybersecurity, Institute of Aeronautical Engineering College. So, in the last previous sessions, we discussed about different types of algebraic properties and different types of algebraic system structure. In that system structures, groups and types we discussed. So, today we are going to discuss on the next session on rings. So, rings are the concept. So, see here the rings. So rings are also a form of algebraic structures. So groups, rings, fields, these are all having different types of algebraic structures. So rings. So today we are going to discuss about rings. So ring is a algebraic structure. Yes, you can say that ring is a algebraic structure, and you can indicate a ring as this square shape. Suppose if you indicates group as a circle shape, then you can indicate ring as a square shape, right? So square shape. So a structure, a ring is a structure. A ring is a algebraic structure denoted with r, comma, plus, comma, dot operator. R, comma, plus, comma, dot operator. So r is nothing but a ring, and plus, comma, dot r, plus, comma, dot are two binary operations. So then it is a ring if R is a non-empty set, or is a non-empty set. That indicates it have some elements. It is a order of a group, order of a ring also. So R is a non-empty set, and plus and dot are binary operations. Plus and dot are binary operations. See, you can indicate like this for the plus operation. The ring R into R, that is nothing but A into B or A plus B. You can take any of them. So R into R belongs to R, A comma B. That means the elements of A comma B with the respective of addition belongs to the R, and similarly the elements of A comma B with respect to the multiplication operator belongs to R. That means the ring contains A comma B elements, and that A comma B elements are performing this addition operation as well as dot operation. So dot operation is nothing but multiplication operation. So the binary operations, both plus and multiplication, performs on ring. So these are the two operations. So if you want to set that a ring, so you need to show some properties that to be satisfied. So you need to show that some properties to be satisfied. So for the addition, R plus is an abelian group. That means R plus with the respective of plus operator, that ring is to be abelian group, and that is associativity property it should satisfy. The elements of ring contains any of the numbers, that is nothing but non-empty set. That is nothing but non-empty set, and it can have all the different types of elements. And here the A comma B comma C, you can take any of A comma, this is A value, and this is B value, and this is C value, you can take. So the associativity property is what? A plus of B plus C equals to A plus of B plus C. So you can pronounce it as A plus of B plus C equals to A plus B of plus C. So this is nothing but associativity property. So you can satisfy, if you satisfy them, 1 plus of 2 plus 3 equals to 1 plus 2 of plus 3. So the result is what? 1 plus 2 plus 3 is nothing but 5. That equals to 1 plus 2 is nothing but 3 and plus 3. Right, so 1 plus 5 is nothing but 6, and 3 plus 3 is nothing but 6. So it satisfies, and this 6 is belongs to the type of a ring, integer, type of a ring number, you can say that anyway. And 0 element is nothing but identity element. So it should satisfy associativity property along with the identity property also. So identity property is nothing but A plus 0, A plus. So 0 means what? For the addition operation, the identity element E is 0. The identity element E is 0. So that's why A plus 0 equals to 0 plus A, that equals to A. 0 plus A equals to A. And for the inverse operation, So for any A belongs to R, there exists minus A belongs to R. As we discussed in the groups also, same the thing will happen here. So minus A belongs to R, that is nothing but with respect to the addition operation. Minus A is the inverse to the A. So that's why minus A plus A equals to 0. The result of inverse operation is to become a 0. And next, commutativity property. So commutativity property, we already said that if the group satisfies this commutativity property, then the group is said to be abelian group also. So here a ring also satisfies this property. So for all A comma B belongs to R, then we have A plus B equals to B plus A. If it satisfies this A plus B equals to B plus A that belongs to R, then it is said to be a ring. Then it is said to be ring. So if the structure wants to become a ring, it should follows this all the rules, whatever the followed by abelian group, whatever the followed by abelian group. So those are all nothing but with respect to the addition. And for the multiplication operation, it should satisfy associativity property. It should satisfy associativity property. So for all A comma B comma C belongs to R, then we have to write like this: A dot of B dot C equals to A dot B of dot C. A dot B of dot C. So here the dot operator indicates this multiplication operator. So A dot of B dot C equals to A dot B of dot C. You can pronounce like this way. And addition and multiplication together also. Addition and multiplication together. So this is nothing but you can say that a distributive law. So distributive law tells that it takes two operations. It takes two operators, plus operator as well as dot operator, and the expression is distributed over that operations. Expression is distributed over that operations. So you can write it as A dot of B plus C equals to A dot B plus A dot C. See here, A dot of B plus C equals to A dot B plus A dot C. That is distributive over the plus operation as well as dot operation. Similarly, see here, A plus B of dot C equals to A dot B plus B dot C. So this is the way you can distribute it over these elements. This is over these elements. So with the addition operation, with the respective of addition operation, what it should satisfy is addition operation, associativity satisfies, and identity should be satisfies, and the inverse should be satisfies, and the commutativity property satisfies. If these four properties be satisfied with the help of addition operation, then it is said to be ring. As well as with respect to the multiplication, it should satisfy associativity property as well as distributive property also. So distributive law tells that it performs operations over the plus and dot operations. Both it can take. So this is the way you can see that multiplication operation. And now the types of rings. So now up to this ring concept is I think clear. And types of rings you can see here. And as like groups, we can have different types of subgroups, different types of semi-groups, monoids, cyclic groups, and all. So like the way types of rings can have two types of rings. So one is commutativity ring and the second one is identity ring. One is commutativity ring and the second one is identity ring. So see here, assume that R semicolon plus comma dot operation is a ring. If you consider that R comma plus comma dot operation is a ring, we say that R is a commutative ring if its multiplication dot is a commutative. If this multiplication dot is a commutative. See the previous one. So commutative is nothing but A plus B equals to B plus A. Then we can say that it follows commutativity property, right? So see here what it tells that A dot B equals to B dot A if it is satisfied for all A comma B belongs to R, then it is said to be the commutativity ring. Then it is said to be commutativity ring. So it is one type of ring. So it is one type of ring. If a ring is satisfied commutativity property with the help of dot operation, then it is said to be commutativity ring. As we discussed in the previous abelian group also, so if it satisfied a plus b equals to b plus a with respect to the addition operation, then it is said to be abelian group, right? So same way here, the dot operation is distributed, or the dot operation is performed on a dot b equals to b dot a. B dot a belongs to ring, then it is said to be commutativity ring. And next one is identity element or identity ring. So identity ring is nothing but there exists, so it performs identity operation e equals to 1 on what? A dot e equals to 1, a dot e equals to a. So that means it performs dot operation as identity element. So a dot 1 equals to 1 dot a, and that means 1 belongs to R. It should be follows that 1 should be belongs to ring. So then it said that identity ring. So if it is not there in the ring, the one element is not there in the ring, then it is not said to be identity ring. If the one is in the ring, then it is said to be the identity ring, right? So here the identity element is what? 1. So identity element is 1. So this is the way you can understand this type of rings. So one is a commutativity ring and second one is identity ring. So that is a ring concept, and you can see some calculation rules for the rings. So how you are going to calculate the values, calculate the rings means you can follow this some formulas. So assume that R comma plus comma dot is a commutativity ring. Commutativity ring is nothing but a dot b equals to b dot a, or else you can say that a plus b equals to b plus a with respect to the plus operator, with respect to the dot operator belongs to ring, then it is said to be commutativity ring. So see here, let a comma b comma c, then what will have? A plus b equals to a plus c, a plus b equals to a plus c, then b equals to c, it is getting like what? So left cancellation law. So as per the left cancellation law, a and a should be cancelled from the both the left side, and the remaining result is what? B equals to c. And next, second one is what? If a plus a equals to a, then a equals to 0. That means you need to understand that a equals to 0 means if you substitute 0 in the place of a, then what you will get? A plus 0 equals to a. Obviously you will get this one only, right? So that is why you can say that. And third one is what? Minus of minus a. That means inverse of inverse integer. That is nothing but normal integer is what? A, and the inverse integer is what? Minus a with respect to the addition. So for this a integer, the minus a is the inverse integer. So what we are saying here? Inverse of inverse integer. So inverse of inverse integer equals to a. Inverse of inverse integer is equals to the normal integer. So that is nothing but minus of minus a equals to a. And 0 dot a equals to 0. That means identity element is what? 0. But the respective of multiplication operator, if it wants to become a positive integer, the identity element is 1. Then only you will get the positive integer as a result. But whenever the identity element becomes 0 with the respective of multiplication operation, then the result is also getting 0. So 0 dot a equals to 0. 0 dot a equals to 0. And next one is what? Fourth one, minus a minus of ab. Minus of ab, you can write it as, you can write or you can rewrite it as minus a of b equals to, or you can rewrite it as a of minus b. A of minus b. This, in this way you can write and any of the problems. So if you find this as a statement, if you find this as a form, and you can reform into this way or this way, you can reform it as in this form or this way, right? And next, assume in addition that R has an identity 1. So these are all we'll say that calculation rules. And here the addition with respect to of addition, minus 1 dot a equals to minus 1 dot a equals to what? Minus a. Minus 1 dot a equals to minus a. So here the inverse identity, the identity nothing but 1 dot a, this is nothing but inverse identity. You can say that minus 1 dot a equals to minus a, minus 1 dot a equals to minus a. And next, if a belongs to or has a multiplicative identity, or has a multiplicative identity, then a inverse. So if a is a multiplicative identity, then a inverse, then ab equals to 0. Then ab equals to 0. That implies b equals to 0. That implies b equals to 0. That is nothing but simply a dot a inverse equals to 1, but a dot b equals to obviously 0, because b is not an inverse. B is not an inverse of A, right? So we already said that in the abelian groups also. So a dot a inverse equals to 1, it is true, but a dot b equals to 0 obviously, because b is not an inverse. B is not an inverse of A. So like the way you can apply in some forms. So this is not inverse to this A, and that's why we can mention that A inverse is a multiplicative identity to the this positive integer, to the positive integer A. So that's why A into A inverse equals to 1 will come, but irrespective of A inverse, A into B equals to 0 you will get. A into B equals to 0 you will get. So these are the some calculation rules for the rings. So a dot b and b dot a plus b, so commutativity ring, and it follows commutativity ring with respective of multiplication operations as well as addition operations, So these are the calculation rules. That these calculation rules you can apply only on problem solving of any ring forms, So the next one is subrings. So already obviously we said that a group can have a number of elements, and a subgroup is also can have the same number of elements belongs to the group. So whatever the group satisfies all the properties, the subgroup may have that satisfies all the properties. So the same way the rings and subrings also following that forms. So subrings. So let R plus dot be a ring, and let S be a non-empty subset. Suppose you can take R equals to this is a ring form, and here you can mention 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and from this ring you can create another subring S equals to 1, 4, 6, 8, 10. You can form it as. So this is, so whatever the properties having that rings can have also to this subrings. So then S plus dot is a subring of R if it is a ring with respect to the operations it inherits from R. So this is what we are mentioning here. The R is a ring can have the some properties, and S is a subring. It is also a ring which acquires the properties from ring. So this is what we are going to say here. And if you want to test this as a subring or not, you can mention here. So let R be a ring and let S be a subset or equals to R. S subset in nothing but it is also included. It is also included as a part of the ring, as a part of the ring or as a ring. So you can take S subset or equals to R. S subset or equals to R. Then S comma plus comma dot is a subring of R if and only if that S is non-empty, that S is non-empty and the following forms hold. The following forms should be held by the subring. So what are that following holds? A plus B belongs to S. It should have A plus B belongs to S, and it should have A minus B belongs to S definitely, and it should have A B belongs to S. A B belongs to S. So for any A comma B belongs to subset. A comma B belongs to subring. A comma B belongs to subring. That means it follows A plus B form, and it follows A minus B form, and it follows A dot B form also. If satisfies them and the result is again a subring can have the elements, then it is said to be subring. Then it is said to be subring. So like the way you can perform the testing on subring. You can perform the testing on subring. So this is the way you can understand the subring concept. And next one is quotient rings. So quotient rings. So this is also a type of rings. So we already said that a group can have different types of groups. Similarly, a rings can have different types of rings. There is nothing but subrings and quotient rings, right? So let I be an ideal. So let I be an ideal. So ideal is also a type of subring. Ideal is also a type of subring. And this let I be an ideal of ring. So we will define ring, which we call the quotient ring. So if any ring is become an ideal, if any ring is became an ideal, then that ring is said to be quotient ring. Then that ring is said to be quotient ring. That means the ring may have subring or not, no problem, but the ring should be ideal. The ring should be ideal, and that ideal ring is nothing but quotient ring. Quotient ring. So which we call the quotient ring or factor ring. So you can call it as quotient ring or factor ring also. That means suppose you can take any of the ring or any of the subring can have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So take any element of 8 and the subring you can take suppose 2, 4. Then you can divide 4 and 8. So 4 to 8, it divides, right? So it divides. So this ring is whatever this element is in this subgroup, then it is said to be quotient ring or factor ring. So these are all the ring elements, but these are the factor rings that elements. So you can say that subring, and this is nothing but quotient ring. So which we call the quotient ring or factor ring of R by I. This is what we mentioned here. This is R and this is by I. So R by I. So that denotes by R by I. Right. So the elements of R by I are the cosets of I in R. Cosets of I in R. So we already discussed that cosets concept, right? So in that cosets, so whatever the elements that are divisible to this entire group, so subgroup is divisible to the entire group, then those are said to be cosets. And for the left side, left cosets, and for the right side, right cosets. That is what we studied in the previous session, right? So similarly here, R by R the cosets of I in R. Thus each element of R by I is a set of elements. So R by I is set of elements is nothing but this is what. So suppose if you can take R by I equals to this 2 is divisible to the 2, right? 2 is divisible to the 4, right? 2 is divisible to the 6, right? 2 is divisible to the 8, right? 2 is divisible to the 10, right? So this is all a subset. This is all a subset. That is nothing but the each element of R by I is set of elements of R. So these are all belongs to this R. These are all belongs to this R. So this is the way you can mention that point. So remember that each coset can be written as. So you can write like this way. I plus A for some A belongs to R. I plus A for some A belongs to R. So we have to define this addition and multiplication law. So I plus A plus of I plus B equals to, you can rewrite it as I plus of A plus B. So you can elaborate it, A plus I plus A plus I plus B. Right? In the same way, you can write this one also. So I plus A into I plus B. That is nothing but you can rewrite it as I plus of A dot B. You can write. So if you elaborate this statement, definitely you will get this one, I plus A dot of I plus B. So see here, I plus A dot I plus B. So with the help of these operations, you can perform addition and multiplication on these quotient rings. So quotient rings are nothing but the ideal of the rings. Whatever the ideals of the rings are called as quotient rings. And you can also say that quotient rings are also factor rings. So R by I divides all the elements of the R. Then R by I maintains the separate elements as a set. So this is what R by I here. And next one is what very important one. So concept of homomorphism. So this homomorphism and isomorphism can be applied on both groups, rings, fields, and anywhere. So algebraic structures and algebraic forms, algebraic structures or algebraic systems can use this all the properties. That is main important property, homomorphism and isomorphism. So see here, what is meant by homomorphism? The name itself, homo means same. But iso means different. See here, consider you can take any of the two groups. So one is G and the second one is G1. So G contains some elements and G1 contains some elements. Right? So a function f G tends to G1. Is called as homomorphism if and only if f of A star B equals to f of A plus R. This indicates plus or multiplication. So it indicates both plus operation as well as dot operation. Right? So G tends to G1 is called, suppose G is a group, can have 1, 2, 3, 4, and G1 is also having same 1, 2, 3, 4. Then each and every element is matching with these two groups. Then it is said to be homomorphism. So that means the group G contains elements and group G1 contains elements are to be same, and they should perform this operation also. So this indicates both plus as well as dot operation. And see, and next, if a isomorphism is what? So if a homomorphism of F tends to G1 is a bijunction. Bijunction is nothing but diversion isomorphism. So that means difference. So this is G contains 1, 2, 3, 4 elements, and this is G1 contains different elements like 5, 6, 7, 8, 9. But while comparing these two groups, the order of this group is what? 1, 2, 3, 4, 5 means 5. The order of this group is what? 5. And this order of this group is also 5. So the same elements is nothing but countable elements. The number of countable elements belongs to this countable elements for the next group. Countable elements for the next group is also same. Then you can set that it is a isomorphism. So simply you can say that bijection of homomorphism is nothing but isomorphism. So bijunction is nothing but diversion. Diversion is nothing but differences, but the same order. It should follow same order. So here the 5 elements and here the 5 elements, but the elements are different. The elements are different, but order of the group is same. Order of the group is same. So then we can rewrite it as G congruence to G1, G congruence to G1, G congruence to G1. So this is the way you can understand this homomorphism. So homomorphism means the elements of the group 1 and the elements of the group can contain same elements, and it performs f of a plus b equals to f of a plus as well as dot b. That means it performs both operations on that group, so that it is said to be homomorphism, right? And second one is what? Isomorphism. So isomorphism in what? The bijection of homomorphism is called as isomorphism. That means the elements contains the group and the elements contains the group 1 may not be same, but the order of that group and the order of that group 1 is to be same. Then it is said to be isomorphism, and you can mention it as a G congruence to G1 or G equals to G1, as you can say that. So this is the way you can understand this homomorphism and isomorphism. So we will see one example. So let R be a group, R be a group of all real numbers under addition, of all real numbers under addition, and R plus B a group of all positive real numbers. So R is a group of real numbers they are considering here. R is a group of real numbers, and R plus is a group of all positive real numbers, under multiplication, here under addition, So R is a group of real numbers under addition, and R plus is a group of positive real numbers under multiplication. Show that the mapping of f tends to R plus is defined by f of x equals to 2 power x for all x belongs to R is an isomorphism. So we need to show that as a isomorphism. So isomorphism means what? Bijection of homomorphism. Bijection of homomorphism is nothing but bijection of homomorphism is nothing but isomorphism, right? So see here, first of all let us take we need to show that it has a homomorphism. So what we'll get? Let a comma b belongs to R. So taking the two variables a comma b, and that belongs to R means R is a group of real numbers. So that's why a comma b belongs to R means real numbers. Now f of a plus b, you can have this f of x equals to what? 2 power x. So f of a plus b is nothing but addition of, under addition you can say that, right? So under addition means f of a plus b equals to f of a plus b equals to, substitute this a plus b in x, then you can rewrite it as 2 power a plus b. So you can rewrite it as a 2 power a into 2 power b. So 2 power a is nothing but what? F of a and f of b, 2 power b. So you can rewrite this 2 power a into 2 power b as f of a dot f of b. So this is what we have to show this in the homomorphism, right? So whenever the f of a plus b equals to f of a dot f of b, then it is said to be the homomorphism. The multiplication of this f of a dot f of b is become f of a plus b. So now it is shown that homomorphism, right? Next, let us prove that f is a bijection. So what we need to show? Actually isomorphism, we need to show it as isomorphism. So isomorphism means what? Bijection of homomorphism. So here we shown that it is a homomorphism. Now we want to go to show that bijection of homomorphism. So see, let us see here. So for any a comma b belongs to R, let bijection is nothing but the order should be the same. But the different elements. So f of a equals to f of b, we need to show it. So we already said that g congruent to g1 or g equals to g1. So if it is, then it is a bijection of homomorphism, and also you can say that it is a isomorphism, right? So here we are going to show that it has a bijection of homomorphism. So it is a homomorphism. Bijection is nothing but g equals to g1 or f of a equals to f of b, we need to show. So 2 power a equals to 2 power b. So f of a means what? 2 power a, and f of b means what? 2 power b. So 2 power a equals to 2 power b, then you can cancel both 2 here, and you can say that a equals to b. A equals to b. So then it is said to be f is, the function f is 1 to 1. So 1 to 1 is nothing but f of a tends to f of b. So f of a tends to f of b is nothing but 1 to 1. The order should be same, but the elements should be different. So next, take any c belongs to r plus. C belongs to r plus. So r plus means r plus means what? Group of positive real numbers. Group of positive real numbers under multiplication. Under multiplication. So c belongs to r plus, and here log 2c, log, you can rewrite it as log 2 base c belongs to r, and f of log 2 base c equals to, you can rewrite it as 2 log 2 power a means, so 2 power log 2 base c, you can rewrite it as. So then what is the value you will get? C. You will get final value is c. So every element in R plus has a mirror image or prime image, pre-image in R. So each and every element in the R plus is a pre-image of R. So every positive real number in group 1 is ring 1 or group 1 is belongs to the same group, we are saying that. So every element in R plus has a pre-image in R. So that is f is onto, that means it contains the same image on that group or that ring, you can say that. So f is onto. So if f is 1 to 1 and f is onto, then you can say that f is a bijection. F is a bijection. So if it becomes bijection of that homomorphism, it is directly considered that it is a homomorphism. Directly can say that it is a homomorphism. So f is a bijection, and hence f is an isomorphism. F is an isomorphism. So this is the way you can understand this isomorphism and homomorphism. Isomorphism and homomorphism. So actually we need to show what isomorphism, but if you want to show that isomorphism, you need to show first of all homomorphism. After showing that homomorphism, you need to show what? Bijection of that homomorphism. Bijection of that homomorphism means what? Bijection is nothing but it should become 1 to 1 as well as onto functions. So if it is 1 to 1 then onto functions, then it is automatically, it becomes like bijection of that homomorphism. So now it is said that homomorphism and isomorphism, right? So this expression, you can say that it is a isomorphism. You can say that isomorphism, right? So these are the rings. These are the concept of rings. We are talking about rings and subrings and quotient rings in this session. So that's all enough for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.